All right, this is the start of our very brief unit called complex numbers. We're going to discuss what they are and what they mean. Today we're starting with simplifying and graphing them. So, to reduce complex and imaginary numbers, first you have to recall how to reduce regular radicals, because complex numbers are radicals. So remember, when you do that, you generally break it up into two radicals, the perfect squares and the leftovers. Some people like to say good house, bad house. I don't really care how you talk about it, but the first one is your perfect squares. So let's just recall quickly perfect squares. Number perfect squares are 1, but when we're reducing, 1 doesn't really count, but it's still a perfect square, don't forget. 2 times 2 is 4, 3 times 3, 4 times 4, 5 times 5, 6 times 6, 7 times 7, 8 times 8, 9 times 9, 8 times 8, I forgot that one. Ooh, 64. 9 times 9, 10 times 10, 11 times 11, etc. There we go. 13 times 13 is 169. So what we do, this 2 stays out in front. Brief recall. Anything that's perfect square, so we look at 75, do any of these numbers divide into 75? Well, there might be more than one. So what we always do is we look, okay, 75, if this was a number line, and I just put these numbers on the number line, 75 would fall right about here. So what we do is we pick a number below it and we see if it divides evenly. So having your calculator out is definitely a good idea. So you take 64, divide it into it. Does it divide evenly? No. And then you just work your way down, because you always want the largest perfect square. Okay, because sometimes there's a bunch. Always look for the largest. So in this case, 25 is the largest, so that goes out in front. So 25 times what is 75? Well, it's 25 times 3. So these two multiplied together always has to equal that. Then you take the square root of 25, which is 5. And remember, this is one giant multiplication problem. This is multiplying, multiplying, multiplying. So this is 2 times 5, which is the square root of 25, times radical 3. This is always multiplication. Hello, I am multiplying. Okay? So same deal here. 3 times radical 49. Well, if you look at it, radical 49, oh, look at that. It's a perfect square. So what is the square root of 49? Well, it is 7. So 3 times 7 is 21. That's it. Remember, when we have perfect squares, if it's a letter or a variable, exponent has to be even. So when I break this up into perfect, good house, bad house, whatever, the perfect square that divides into 32, I know 4 does, but 16 is bigger. Okay, so that's what I mean by finding the largest perfect square. It's easier if you start with the highest number it could possibly be, which is 25, and work your way down than just going with the first one that you think of. Okay, so I always do it one little section at a time so that I don't forget stuff. So 16 times what is 32? 16 times 2 is 32. So x to the 4th, well, that's an even exponent, so that's a perfect square. It belongs there. Y to the 7th is not. But if I go down one step to y to the 6th, it is. So y to the 6th times y to the 1st is y to the 7th. So you simply go down one and you get a perfect square letter. So we take the square root of this. So that would be the square root of 16 is 4. Remember, divide each of these exponents by 2. So it's x squared. Y cubed, remember this is multiplication. And radical 2y stays right there, so it winds up being 8x squared y cubed radical 2y. Right, we're going to do a little practice with this. However, it's not exactly something that we should be doing because it is review. Okay, so break this up. Good house, bad house. The square root of 16 is a perfect square. so we don't need to put anything in the other one. X squared is a perfect square. Y to the 9th is not, so we put 1 down, y to the 8th, with 1 left over. And then we simply take the square root. Square root of 16 is 4. Square root of x squared is x, and y to the 8, remember, divide those exponents by 2. And radical y just stays there. So it's 12x, y to the 4th, radical y. Be careful here. Once you take the square root, we don't take it again. Okay? So take the square root and you're done. So that's just a reminder of how to reduce radicals. You are going to be doing a lot of it. So for example, you're going to be reducing radicals with a negative underneath. So when you have a negative underneath, it's what we call I. This is where complex numbers comes into play, an imaginary number. So an imaginary number is when you take the square root of -1. So the square root of -1, or plus or minus in this case, the square root of -1 is I. So that's it. I is the square root of -1. So it basically just gives us a little shortcut into how to reduce these radicals. Right, to reduce this, all we do, if we have a negative under the radical, it simply means there's an I on the outside. So I'm going to write this way once. Okay, so I could multiply -24, right here, is equal to -1 times 24. This isn't really the reducing part, but it's just to show you that if I want this to be positive, which it has to be for us to really do anything, I can't have this negative. So I just take the negative out, and that's like the I, rip the I out. It's close to Halloween. It's a nice visual right there. Take the I out, and now we just have a 24. Now you treat I just like a variable, and there's nothing more to it. So then we just break it up. -2i times 2, radical 6, and it's -4i, radical 6. So over here, I did show you how to write an imaginary number. So when you write an imaginary number, the number goes first, then the I, then the radical. Okay? Some people don't mind if you put the I over here. I hate it. So, when you're in my class, I guess don't, because that if you put an I there, sometimes it looks like it's under the radical. Okay, so please, number, I's, and any other letters that might be involved go there also, and then the numbers. So same deal that happens over here. So this is how I basically go through it. Instead of doing that whole mess with the 24, I say, okay, there's a negative under the radical here, so let's just make it positive and put an I right here. So it is 4i radical 64. Sometimes it's easier to see that, okay, because it's simple. Okay, the square root of 64 is 8, so it's 4i times 8, so that's 32i. Here, same idea, the negative on the inside just does that. The negative on the inside is not related to the negative on the outside, so don't make it. Okay, then you just reduce. This is 81 times 2. And then it's negative 9i radical 2. Okay, so complex numbers. When you have complex numbers, they have a real part and an imaginary part. So the A is the real part, the B is the imaginary part, or the BI is the imaginary part, but A and B are real numbers. So here, for the first one, the A plus BI form, A is 2, and B is the thing that's next to the I. Then this one, A is 6. What's next to the I? Well, there's nothing next to the I, so that would be just 0. Over here, what would A be? Well, you would have to divide that 2 into both pieces. So it would be 5 over 2. That's 5 over 2. And then 10 divided by 2 would be 5. So we would rewrite this 5 over 2 plus 10 over 2i, but 10 over 2 is just 5. And then 3i, well, that means that there's no real part, so that's 0. There's no A, and then B is 3. So looking at this helps you graph it. I'm sorry it's taking so long. There's a lot of stuff in the first video. So when you graph it, we don't graph it on the XY plane here. We graph it on the I don't know why it does this. We graph it on the A, BI plane. So it's basically saying the A is your X and the B is your Y. So this is simply like graphing the point 2, negative 3. So when we do that, we go 2, negative 3. So that would be right about here-ish. And then we draw a little vector right there. Vector. All right, starts at the origin and goes right to that point. Same deal with this one. Negative, we would plot negative 3, 2. So negative 3, positive 2. And then we start at the origin and graph that. Probably a good idea to label each one. Negative 3 plus 2y. All right, have a good day.